Okay, we can get started with the first talk of the morning. The speaker is Michele del Zotto, and he will be telling us about symmetries, anomalies, and geometry.
Thank you. Thank you very much for the kind invitation to this wonderful conference. And it has been a pleasure to meet you all while we were here. And it has been extremely hectic and extremely exciting for the many developments that we have seen. So yes, thank you. Thank you very much for putting this together. I will talk today about some interplay between symmetries, anomalies, and geometry, which is based on a series of works. A couple have appeared earlier this year. Shani Mainet is a postdoc in my group. Moskrop was my former PhD student. And then another one with Federico Bonetti and Ruben that don't need presentation here. And then another one which is in progress with my now PhD student Elias Riedel-Gorning and Azim Hassan, who's another postdoc in the group at Uppsala. So of course we are building on the shoulders of giants, and there are a lot of key work in the subject. And many from the strings and geometry community. So I want to signal the group in Durham, where we have heard talks by Iñaki. Federico is based there, Tom is there, has worked on this subject. At Johns Hopkins, there is Ibu and his group that are working on this. In Oxford, most notably, the group by Sakura, where a lot of work and excitement about this topic has sparked. And also in Penn, the Miriam and Jonathan, Max, Ethan, that now is at Tern, like all these people deserve credit, and I want to Fabio, Francesco, a lot of work from our community, and also many more from people that are more field theory oriented, like Kantaro Mori or Clay Cordova, Thomas Dumitrescu, a lot of references. I'm sorry, I wasn't able to add the references on the talk because I met Kumrun at breakfast. It was an exciting conversation. I couldn't leave. so yes, let's get started. So we heard several talks earlier in this conference about the higher structure of symmetry. The idea is that we can describe symmetries in quantum field theories in terms of topological membranes. So membranes that have no displacement operator. We can move them around as we please. We can slide them around time. We obtain defects. We slide them around space. We obtain operators. They act on states, and they give rise to interesting constraints. We've seen in Jonathan's talk the linking action. There are other types of action related to crossing. You can cross a lower dimensional non-topological defect with a topological one, and it transforms, or you can take it and move it through, and it will transform in a slightly different way. It can leave behind some further topological membranes that remembers that it has crossed. This is essentially an analog of the Hanani-Witten transition, as was pointed out in papers by people in the audience. So the main mantra here is that we should think about symmetries not in terms of group, but in terms of categories. No? That's the most natural framework where we can describe these topological membranes. And the objects are quantum field theories themselves, no? And the morphisms are topological membranes. So all topological membranes are morphisms. If you have a given fixed quantum field theory, the symmetries of that one are essentially described in this language as the endomorphism of the identity for that specific object. So don't be scared, because this is really literally about building interfaces. So you have a topological defect, you have another one, you build an interface between them. As long as this interface is topological, that describes a morphism in the higher category. No? And of course, if you have two different ways of going from D to D prime, say an interface M and an interface M prime, you can add a morphism between them that connects them. And that will give rise to a higher morphism, a morphism between morphisms. No? So this is what gives this symmetry category the structure of a higher fusion category, a higher fusion category, or slight generalization thereof. No? So to fully specify the symmetry, the lesson of this is that to fully specify the symmetry of a quantum field theory, we need to give more data. It's not just enough to give me the group. You have to give me all the morphism, all the stuff that goes in between. No? That's this more data is what is kind of interesting about this development. So, for instance, I give you a defect, it arises as the fusion of two, there is a morphism between them, but the morphisms are not all that there is. So, for instance, you can consider bringing in three defects and doing it in the opposite order on the opposite side. So here there are, I don't know, D1 and D2, 3 that fuse and give D. There is D2 that comes with D3 and gives D2, 3. But here we can think of D1 and D2 that fuse together and goes back, and D3 that fuse with this one. And they give rise to a channel, a fusion channel, from D to itself, no? A map from D to itself. And since this is all topological, we can think of shrinking this down to a point, no? And we obtain an interface of D from between itself, and this interface measures the associativity of the fusion product. You see, here I'm bringing D1 and D2 first together, and then I'm adding D3, and instead here I'm bringing D2 and D3 first together, and then I'm adding D1. No? So if I shrink this bubble, I obtain something that captures the associativity of fusion. No? If you are in 2 dimensions, this is a plane, this is what happens, this is a faithful description of this fusion of things, topological membranes. This is just a number, no? Because it's something that is a point. It doesn't have much room to do much more. No? But in higher dimension, this can become higher dimensional membranes, and so this thing is no longer a number, is a topological membrane of its own. No? And this topological membrane, again, measures the associativity of the fusion product. No? So this is an example of the extra data that we need to specify in order to fully give the symmetry category of a quantum field. No? There are all these topological membranes that explain how to fuse things together. No? And this topological data is physical. So if you have, for instance, an example of the crossing action that I mentioned before, you can consider inserting a non-topological defect on which this structure would act. And then, since this is topological, we can think of moving it through, sliding it through. No? For convenience of the drawing, I will represent W going up, but you have really to think about this going down. No? So we start sliding, and as soon as this stop, okay. So as soon as this defect crosses the blue ones, it will start to give rise to this crossing action that I described in the first slide. No? We move it through, and you see, whenever it crosses one of these morphisms, we pick up some intersections also on these lines that this defect leaves behind. No? And we can do it. We can move it through. And as we have moved it through across the whole thing, no, we get a complicated network of lines, points, and all these data, when we shrink, becomes a vertex insertion in the two-dimensional topological field theory that we have here. So the fact that there is a non-trivial action coming from the blown-up description implies that it has to be compatible with the fact that this correlator is non-trivial. And this correlator is what captures the action of this part of the higher structure of the symmetry on the extended defects. So this data is physical. You can measure it, this higher structure of the symmetry. It's not something that is just there for beauty. It's something that has really an effect on correlators. And we tracked this down in simple examples. So we computed it for a massless QED, for instance. We checked that this is non-trivial, and we computed how it acts. Of course, this is interesting because it gives rise to features like anomalies or higher anomalies. The higher structure is tightly related to anomalies. And as anomalies, it has to match along RG flows, and therefore it gives a finer resolution on the infrared phases of the quantum field theories. No? So this is interesting, but how do we compute it? No? How do we go about computing it? There are various approaches. No? So one approach is I name it topological interfaces. One is a word volume approach, and one is this SymTFT that we've heard about during various talks earlier in this conference. So how do you work with topological interfaces? It's relatively simple. No? You remember that I told you that objects of the symmetry category are quantum field theories, and the first morphism are just interfaces between them. So I have topological interfaces between them, but sometimes it can happen that I compose them, and I get an interface between T and itself. No? So this is an example of a topological interface between T and itself that is not just an ordinary symmetry. Often you can build them in this way. As an example, you can consider as I1 the operation of doing the gauging of a finite symmetry over half space, and this would give rise to a T prime in this diagram, which is just T modulo G, the gauged version, or bifolded version. And then I2 would be a duality, a different isomorphism between this theory and T. So composing them, you get an example of a duality defect. Now, there is the word volume approach. The word volume approach, I'm going quick here because I'm talking to this community, and you all know that we can study membranes, D-branes, using their word volume theories. This is essentially the same philosophy. You study the possible TFTs that you can couple to your bulk, and you study their word volume. And from the word volume perspective, you can recover the junction of the membrane or the Hanani-Witten transition. This is essentially the same philosophy. And then there is the SymTFT, which we've heard about, but will be also the protagonist of part of this talk, so let me emphasize some aspect of it. So the SymTFT, as we've heard during the talks, for instance, the talk by Jonathan yesterday, is essentially comprised of 4 data. No? The first one is an isomorphism, the second one is a relative field theory. This theory is relative to a bulk D+1 dimensional topological field theory. And then there is the fourth one, which is a gapped boundary condition. Now, since this one is topological, bringing this to that one, we obtain this isomorphism, and we obtain an absolute theory, a theory that doesn't depend on a bulk. No, a relative field theory is just a bulk boundary system. It's not something that exotic. It's just something that makes sense defined respective to a bulk. No? So, like from this perspective, as we heard yesterday, so if you have a charged operator on the theory that you're interested in, that one becomes a boundary condition for a topological defect in the symmetry TFT, and the action of the symmetry is captured by those topological defects that exist in this theory that coexist on the boundary. And it is really the boundary that captures the symmetry. This is an important point that was emphasized in work by Sakura and Laksha Bardwaj. So this picture is giving rise to a whole holography of symmetry, some sort of topological version of holography. No? And so what I want to remark here is that it is important that in this picture we have a split between a part which you can think of as if it is the group, and another part which you can think of as if it is the representation. So on this side, everything is topological. There is the topological defects of the topological D+1 dimensional TFT. There is the gapped boundary condition, and there is this action of one on the other that all happens on the topological side. This is the group. No? The isomorphism and the data of this relative field theory, this one is the representation for this group on this theory. Okay? So this is like a group theory, so we can use special examples, like supersymmetric examples, to learn about structures that happen here, but the results then will be general, because as long as the symmetry TFT is the same, then all the topological manipulation happen on this side. So we can use tools from supersymmetric field theory and string theory to build symmetry TFTs, and everything that we learn here can be imported in non-supersymmetric field theory. No? So this is a big application in the context of geometric engineering. This is something that we have heard a lot. So this idea that we have heard in particular in the talk by Iñaki, that exploiting some version of geometric engineering at infinity, you can assign to the link of the singularity a topological field theory that you build out of a geometric engineering at infinity. No? Then, like, the main idea is that whenever we perform a geometric engineering procedure in string theory, what we obtain is not an absolute theory, it's a relative theory. It's exactly this relative theory. And the choices of boundary conditions that we can place on the link of the singularity, they correspond to the gapped boundary conditions of this theory. Of course, there are examples in string theory where we know that gapped boundary conditions don't exist. For instance, the 62,0 theory. But nevertheless, we can perform this geometric engineering at infinity and realize the 2,0 theory is a relative field theory, as we all know. So in that case, we would obtain a 7-dimensional Chern-Simons theory in this bulk, for example. No? So this is a useful tool. Another remark is that we can exploit this to study symmetry-preserving RG flows, no? Because if the RG flow is symmetry-preserving, all the topological side stays put, but we change the dynamical side of this map. So we flow from the UV to the IR on the boundary. As long as the flow is symmetry preserving, we can obtain constraints on RG flows, and I will discuss some examples as the talk goes along. And then, of course, it streamlines the construction of interfaces. Like they arise if your topological symmetry TFT has a zero-form symmetry. Whenever that happens, you can insert it. And now, of course, this is topological, so I can bring it on the boundary. I obtain another one, and that one gives rise to a new theory when I perform this isomorphism. And now, if this boundary has a topological boundary on its own, then I can end it, and by this isomorphism, I obtain from this topological boundary here an interface between the theory I started from and this new one that I obtained by modifying the boundary condition. Now, of course, if this symmetry of the bulk symmetry TFT happens to also be a symmetry of the relative field theory, then composing this isomorphism, we obtain a duality defect from this theory to itself. No? So this is how, exploiting the symmetry TFT, we can streamline the construction of duality defects. No? So are there examples, many examples from stringy constructions? So let me bring you one that is discussed in the paper with Shani and Robert. Consider the 2A engineering of n equal to 4. No? We know about it from a nice paper by Kumlun on the geometric origin of Monton and Olive duality. No? We take type 2A on a background which is a product of a T2 times an ADE singularity. And this one gives rise to all possible n equal to 4 superior means that have this Lee algebra. No? So the W bosons of this theory will arise from D2 branes wrapping blown up P1s here. And the monopoles will come from D4 branes that wrap the T2 times a P1. No? There are dions from D2, D4 bound states. No? And what happens? You see, we are in type 2A. We can perform two T-dualities on this T2. When we perform these two T-dualities, the D4 gets mapped to a D2, and the D2 gets mapped to a D4 in the dual torus, because like the first duality, this D2 becomes a D3, this D4 becomes a D3. The second T-duality, this D3 becomes a D4, and this D4 becomes a D2. No? So in this way, we obtain the Langland dual group in this geometric engineering perspective. However, in these backgrounds, whenever we are at the self-dual radius of the torus, acquire an extra symmetry. And this extra symmetry, from the perspective of the SymTFT, is exactly the duality symmetry that I was talking about earlier. We knew about it. It's there in string theory. It's the self-dual radius of the torus. And now, the fact that the torus is at self-dual radius implies this relation on the relative field theory that we start from. And out of this, we can build the non-invertible duality defects in n equal to 4 from this geometric engineering setup. More exciting construction come from classes theories. You can, exploiting the fact that the duality group there is realized in terms of the mapping class group of the Riemann surface. We have heard about classes theories in the talk by Jacques a few days ago, so I'm quick about this. But like fixed points of the mapping class group give rise to generalization of the self-dual radius of the torus, and then we obtain many generalizations of this type of construction. They will be useful for the example that I will speak about later. So how about anomalies? This is another part of the title. Anomalies have two manifestations. They can be thought of as obstructions to gauge asymmetry, or as obstruction to have a trivially gapped symmetric vacuum. No? These are two aspects of the anomaly that agree for usual symmetries, but can disagree if you have a symmetry category that has morphism with more fusion channels. So when this happens, these two notions don't agree anymore, and this one is stronger than this one. So there are examples of symmetry categories that don't have trivially gapped symmetric vacua, but that still have gaugeable parts. So let's consider first this one. We spoke about the symmetry TFT. We remembered in the talk by Iñaki about the fact that whenever you have some mutually non-local topological defects, this gives rise to different boundary conditions. And the operation of gauging these ones correspond to swapping the boundary conditions that are allowed for the electric ones and the magnetic ones. So this first linking pairing detects this non-trivial Hilbert space structure of the symmetry TFT. However, if you want to detect the obstruction to gauge asymmetry, there was a nice remark. It was known in the condensed matter literature, but imported in our literature in a paper, a recent paper by Emily and Justin and I think also Zafrir, Gabi and Zhang was also involved, where like if you want to detect the anomalies, this obstruction for gauging asymmetry come from having in the SymTFT some non-trivial expectation values for linkings that are of the Brownian kind. So a Brownian link is a link that, if you remove one of the links, become unlinked. No? So in this case, I'm giving an example, and if you remove any of these cycles from here, you will see that you get an unlinked configuration. So looking at the possible configuration of links that you have available in your dimension and computing these expectation values is a hallmark of anomalies, of obstruction to gauge. No? And in geometric engineering, how does this show up? No? In geometric engineering, we've heard in earlier talks that all these topological defects are captured by some topological membranes wrapped on the link of the singularity. So you have to combine these linkings in the SymTFT space with some torsional Higher linking pairings in the link of the singularity. And these are computable. These are extremely computable quantities in geometric engineering, but give rise to some sort of a higher flux non-commutativity, some higher notion of flux non-commutativity that captures these anomalies that obstruct the existence of boundary conditions of this type. And it is interesting to check that whenever you have an alternative description of the SymTFT in terms of other constructions, you do the computation in gauge theory, you do the computation on the geometric engineering side, and the result match. Okay, so there is also the idea that they give rise to obstruction to trivially gapped symmetric vacua. No? How does it work? In this case, you remember, we had this symmetry preserving means that the bulk topological side stays the same and the gapped boundary condition changes. If this one is gapped, then this one must be gapped. But gapped boundary conditions are very special from the perspective of the topological symmetry and can be classified. In particular, if you have a trivially gapped symmetric vacuum, this requires that there is a topological boundary condition of this theory that is such that it can absorb this duality symmetry. No? So you have to check this. This is an algebraic computation. It's very straightforward to do. And in particular, you can also exclude this. So if there are no such thing, then, and you have a flow to the infrared that preserves this symmetry, you predict that the infrared must be gapless. So there are two options, either it's gapped or gapless. If it cannot be gapped, it must be gapless, okay? So this is interesting because, for instance, if you start from class S theories and you work with duality defects that are such that do not admit gapped symmetry preserving boundary conditions, and you can exhibit an RG flow that preserves this non-invertible symmetry along the flow, even if the flow is symmetry breaking, you argue that since there is no possible boundary condition that matches that symmetry that is gapped, the infrared must be gapless. And so you can argue, starting from class S and the duality symmetry construction, that there are other CFTs that are n equal to 1, the one that we know constructed a while ago, the class S theories of n equal to 1 type, but also n equal to 0. So this is an exciting application of this technology. And another comment is, well, this was all about finite symmetries. How about continuous one? Well, again, in this case also, geometric engineering and the idea that we can learn from geometry about the structure of the symmetry TFT comes at rescue. Because we know that, for instance, in holography, if our theory has a global continuous symmetry, that is manifest in terms of a bulk gauge symmetry in the holographic dictionary. Similarly, if you are in geometric engineering, the hallmark of a non-abelian continuous symmetry is a non-compact curve of singularity that extends on the link. So we have a singularity also at the link. So in both these cases, in this case, if you want to extract the symmetry theory, you have to go close to the boundary, and only the topological degrees of freedom in the bulk theory will survive in the limit. And in the SymTFT, again, we have this geometric engineering at infinity, and performing both these operations, which essentially consist of taking this to be very large. No? Performing both these operations, one can extract some topological sectors, some non-trivial topological sectors, out of Yang-Mills theory that look like some non-abelian versions of BF theory, in a sense, with some, and establish some sort of a correspondence between the defects that carry this symmetry and the bulk operators of the topological type that arise from this limiting procedure. So this is good because this gives a bulk boundary description of continuous symmetry as topological defects, and it can be applied to streamline the construction of more general duality defects. It's an interesting construction. It is not good for the gauging process. Because gauging is not a topological manipulation. Gauging a continuous symmetry is not a topological manipulation. Gauging a finite symmetry is. You don't add any new degrees of freedom of your theory if you just gauge a finite symmetry. If you gauge a continuous one, you add the new ones. And so in this respect, one needs to develop a better technology. There were some proposals in terms of some sort of maps between different SymTFT arising from some higher dimensional perspective, some sort of SymTFT with boundaries and corner. No? So this was essentially all I wanted to say. And in summary, like over these years, we are seeing that there is a deep interplay between symmetry structure, Higher symmetry, and their Higher structure, the structure of geometry, of string theory, geometric engineering, and holography, and also anomalies and generalized anomalies. And using stringy techniques to explore this Higher structure is very useful because it can teach us about new features. We discovered these more general duality defects using classes theories, but they can be generalized. We discovered these continuous SymTFTs or symmetry theories. And then, of course, the same disk construction will generalize to theories that don't have supersymmetry. So with this, I think I'm out of time, and I thank you very much for listening.